Let's have a look now at some graph types for data measured at the interval and ratio level. And the first one we're going to look at is the case of a bar chart where we use the bars to display summaries of a ratio variable within categories of a categorical independent variable. So in this example we see, unlike the previous or the first example of bar charts where we were simply showing the frequencies of respondents falling within each case of a nominal or ordinal variable, each category of a nominal or ordinal. In this one, the height of the bar corresponds to a summary statistic for a particular group. So in this chart, what you're seeing is a breakdown of mean internet usage from the European Social Survey. It's split by male, female, and in this case, the height of the bar corresponds to the mean internet usage for this particular group only, and in this case, mean internet usage for this particular group only. So we can see here the average weekly use in minutes for males and for females. What we can do with these then is we can split them up further by different categories, and this is an example of a stacked bar chart where we've got each category basically stacked within categories of a third variable. So now we've got three variables. We've got our outcome variable, which is our internet use, displayed here on the y-axis, and on the x we've got two variables. We've got gender, and we've also got this question measuring the respondent's level of interest in politics. So what we can see here as we move from one type to the other is whether that gender difference in internet usage varies as we look at it within categories of level of interest in politics. I'll talk in a couple of weeks about the notion of statistical control, but essentially what we're doing here is we're looking into other factors that might be influencing how long someone spends using the internet. And one way to start to inspect that is by looking at it visually and looking at graphs like this. So here again we see the height of the bar still corresponds to mean minutes spent using the internet, but now not only do we see the gender difference, but we see the gender difference for those who are very interested in politics, quite interested, hardly interested, not at all. So one thing we could say is that yet average internet use tends to be higher for those with lower levels of interest, but the gender difference seems to be, again, we would probably want to look specifically at what the difference is, and there's other ways we could test this, but the gender difference seems to be biggest for those who are interested in politics. The other type of graph that we can use is a histogram. And we've got a couple of components of a histogram here listed. So on the y-axis, we have typically percentage of cases. Stata will default to show you the number of cases, so we'll have to add something into the code there to get that axis to show percentages. And on the x-axis, we've got values of the variable. In this case, this is national level data, it's country level data, and we've got a variable measuring the percentage that each country spends on health as a percentage of total government expenditure. So what this allows us to do then is to see the spread of values on a particular variable within a particular set of data. So we've got a few different components, as I said, and in this one we need to understand what the different bars are doing. These bars are referred to as bars or bins, and each bin represents a particular range of values. So the width of the bar corresponds to the range of values contained by that bar. So we see here that even though these aren't labeled precisely, and again we don't tend to do this with histograms because we're really looking at sort of the shape and the skew and where the cases might be clustered or which way the graph is tending and so on. The height of the bar again corresponds to the percentage of the cases within that particular range, and we can see here that health expenditure is kind of distributed or concentrated around this particular range of values here, about 10% to 20%. The majority of cases fall somewhere within this range. And this is important again for assessing how representative a particular summary statistic like the mean or the median might be. If there were a lot of cases, say, skewed or concentrated up here in the higher range, then we might want to be a little bit more careful about reporting our mean values as being representative of a typical value in that set of data. So again, we see, although we've got a concentration here in the range of 10 to 20% of GDP, we've got a few countries with particularly high levels of expenditure and probably a couple, it's a relatively small data set, so this bar could be one case or more, in the lower range. And what we can do, and I'll demonstrate this in Stata in a moment, is we can start to vary some of the parameters of this graph. Principally, we can start varying the bins. We can define exactly what range of values each of these individual bins should contain, or we can preset the number of bins that a graph should have. So there's a couple of design decisions we can make to modify this graph slightly. But again, the basic layout remains the same. In the plot region, we've got our bins, we've got a clearly labeled x-axis with our variable name displayed. We've got a y-axis which shows clearly the units, and we've got a title that identifies the variable and generally the source and the date as well. So let's have a look at how we implement this in Stata. So the command that we use to draw a bar chart is we start with the basic root of the graph command, which is graph. To that we add bar, and then we need to define what summary statistic the bars are going to represent. So we see here we've asked in brackets here that the bars correspond to the mean, but we can also ask it to return or to display any number of summary statistics. The most common ones you'll probably need are the mean and median. And what we're going to do here then is we are going to draw a bar chart which is going to summarize household disposable income, and we're going to look at that over categories of tenure. So we want to look at this and see are there any differences between, say, renters and owners and so on. And we've got a couple of settings here that ask for labels and that set the angle of the labels at 45 degrees. So we'll run that and we'll see why that's necessary, because you see here when we've got labels that are quite long like these, some of them can become very long. You always want to make sure that those are angled in a way that makes them legible. And here we see that we have quite a difference in average disposable income between these two groups here, outright owners and mortgaged owners, and quite a big difference between mortgaged owners and tenants on reduced rent, and also between tenants paying market rent. So there's quite a gradient here in terms of tenure and household income. Now you'll remember we discussed in class our summary statistics, and it's worth referring back to that if you're unsure of the distinction between the mean and the median. But a more accurate representation of typical income for a variable like this would be to use the median. And again, if we run it with this, we see that there's quite a difference across each of these different groups. So suggesting to us that tenure is perhaps an important factor to look at if we're trying to explain differences in income. It doesn't tell us why those differences exist, but it does signpost to us that there might be something else going on here. Now, when it comes to a histogram, there are a couple of things that we can do. I'll show you the default version first, and the basic histogram command in Stata, and this is our variable which is PL060, and this is a variable that measures hours worked. And we can get Stata to automate the bins and the width and so on by simply typing histogram, PL and variable name, and then comma % to set the axis. Why this is necessary is that if we run it with just histogram and the variable name, it will give us this somewhat less legible axis units here, which are density. It's easier to read that if we switch it to percentages. So this is showing us again the height of the bar corresponds now to the percentage of cases. So we've got approximately 37% of cases contained within this bin here, and we can see here that this bin contains a score of 40. So it's probably capturing respondents in the data set who work between 39 to 41 hours per week. I'll show you how we can modify that in a moment to be more specific. We've also got a bunching of cases over here around the 20 range, and this is because hours tend to cluster in these two ranges. We tend to in this data set you'll see that we largely distinguish between part-time and full-time employees. Part-time employees tend to work somewhere around 20 hours and full-time employees tend to work 35 to 40 hours. And we've got a smaller number of cases out here in the tails of individuals who are working 60 hours or more up here. So we can modify these graphs a little bit, and the easiest way to get a sense of why we might do that is to show you what happens when we do that. So in this case, we can ask Stata to define the number of bins. And let's say we just want to have 5 bins. We just want to have 5 bars in that graph. If we run the graph with just 5 bins, you can see here that this graph is showing us the same information as before. Okay, nothing has changed in terms of the data that's going into this graph, but what has changed is the level of detail we can see. Now, because it's clustering all those cases into a much wider range of values, we can't really see all the subtleties in that distribution anymore. We can't see clearly that sort of clustering of cases around the 20 and the 40. Even though we see that they're obviously the highest and the clearest bars, we lose a lot of that fine detail by expanding that range, or and again in this case by minimizing the number of bins. If we expand it a little bit more to 35, you'll see we start to recover some of that detail. Again, we can see a little bit more of the kind of complexities and subtleties in the distribution. But there comes a point at which this isn't especially helpful. If we change the number of bins to 80, as you'll see here, we start to get, what happens here is that as we start to expand the number of bins, we could perhaps be getting a bin which is which has a very small number of cases. And again, this sort of reduces our ability to see where some of the key or the main concentrations might be. And you'll see here we start to have gaps in the data as well, because there's probably no case that records a value specifically in the range of whatever this might be, probably something between 37 to 38, or perhaps 37.5 or something like that. So again, we start to see quite large gaps emerging in the data here. So it's perfectly fine to automate this and to default to the automatic for now, but it's just to make you aware that there are these types of things we can do and modifications we can make. The other thing we can do is we can set the width of the bins. So let's say that rather than telling Stata we wanted exactly 35 bins, we could say that we wanted each bin to represent a range of 5. In this case, each bin would correspond to a range of 5 hours, and then Stata would automatically add or include as many bins as were needed to exhaust the full range of hours recorded in that data set. So we see here, if we take the first example where we specify, we say give me a graph with 35 bins, we get something that looks like this. In the second example, we say give us a graph with as many bins, but with an interval of exactly 5 in each of the bins. So each of these bins now represents a range of 5 hours. Again, we see we lose some of the resolution, but we can clearly see there that, again, it starts from 0 to 5, presumably 6 to 10 and so on, in increments of 5. We see the clustering here around 20, and we see the clustering here around 40 quite clearly. So again, we could expand this as much as we wanted. If we wanted each bin to represent 2 hours, we would change the width to 2, and then it would give us something that looks like this. So again, if you're working on these for an assignment or for inclusion in your research, it's perfectly fine to default here to the base command, where Stata simply automates the bin width and count, or if you have good reason to specify a specific interval, again, if there's something maybe meaningful about those intervals, you can always automate that by varying the width. One instance where this might be useful is, I'll give you an example here using household disposable income. So often altering the number or the width of the bins can reveal something more kind of subtle in the distribution of that value. And as we saw in class last week, the distribution of income in this data is very, very much unequal. And if we were to look at the distribution of household income, this is the 2015 Silk data, but the 2019 looks quite similar. We see here that income tends to cluster around here in the lower range, and we've got a smaller number of households up here in the tails with very, very high incomes. But again, that sort of complexity is not really apparent if we work with a graph that has very kind of low resolution or very, very large intervals in the bins, or a very, very small number of bins. If we were to change that, and again, what we've done here is we can generate this graph either by increasing the number of bins. You can see here that there are many, many more bins in the second graph than there are in the first, or we could specify a much narrower width. So we could say that, well, each of these bins should represent increments of €1,000, and then that will automatically give us more. And we start to see here some more subtleties emerging. We see here a little sort of clustering in the 200,000 range, and we can start to see, again, what makes it slightly more difficult to read here is that we can't really see, again, there's so many, there are so few cases in the tails here, these high income households, that we can't really make them out on the graph. But it does show us a little bit more of some of kind of the subtleties of the distribution. Another type of graph that you might see commonly used is what's called a kernel density plot. And a kernel density plot is useful because it kind of gets around this problem of choosing bins and widths, which again can be somewhat arbitrary sometimes. And it does this by, and well, the best way to explain it probably is to show you first of all. So in the case of a histogram, you'll see here what we get is a graph which has discrete bins. So each of these bins corresponds to a very specific range of values. In a kernel density plot, what we have here is in essence a moving window. And what Stata is doing is it's kind of drawing a smoothed line or a curve in some cases around these values using kind of a moving average, and we can vary how that average is calculated by changing the bandwidth, and I'll show you how that works in a moment. So again, if you look at, or if we compare between the histogram plot in the first one and the kernel density plot in the second, what you can imagine this as is kind of it's drawing a smoother line across that range of values in the histogram plot. So a kernel density plot can be useful for several reasons. First of all, because it eliminates some of the arbitrary work around selecting bins and widths, although again we can vary the resolution of this plot. But more importantly, what it allows us to do is to overlay plots, and I'll show you how this works in a moment. So we can vary what's called the bandwidth of a kernel density plot by altering the bandwidth parameter here. And I'll show you the effect that this has on the resolution of the graph. So let's start by, we'll arbitrarily set a bandwidth of 2 and we'll redraw that graph. And we see here that, again, if we compare between the first iteration of this graph and the second, you can see here we've got sort of a slightly smoother graph. Again, what it's doing as we expand this bandwidth is it's smoothing that curve over a progressively larger range of values. So again, following the logic of the histogram, as we expand that bandwidth parameter, we will lose some of the detail, but we will get a slightly smoother curve because it's averaging over more of those subtleties and eliminating some of the bumps. This is useful here because, again, we see there's a bunching around the 40 range and the 20 range, and that comes up quite clearly in the kernel density plot with a bandwidth of 2. But if we start to increase the bandwidth, you can see that it becomes less and less helpful. Now that we've got a larger interval, you'll see we're losing some of that subtlety. And as we go up to a very, very high bandwidth, you'll see that we lose a lot of the detail completely. So a graph like this is completely unhelpful. But again, as with the example of the histogram, for now it's perfectly fine to default to the basic if you want, but it's always helpful for learning to experiment with these and play around with them on your own. Now, as I said, one advantage of this plot type is that we can start to compare groups. Again, these would be sort of grouping variables with a small number of categories. Gender is a good example. So let's say we wanted to compare the distribution of working hours by gender. And the gender variable we see here is, it's RB090, which is the variable name, and it's coded 1 for male and 2 for females. We will encounter this notation again as we finish off our sessions on data visualization, and this is the graph two-way command. And what we're doing here is we are asking Stata to draw a kernel density plot for working hours if the gender variable equals 1, so one plot for males, and another graph. You'll see these two adjacent lines here. We use these quite often in plotting when we want to overlay something or to include something. And we're drawing a graph here for working hours again if gender equals 2, so that's female. And again, we run this together and we see here what we've got is a plot for, this is the male data here, the very, very clear sort of bunching over the 40 range. And the female, the curve for the kernel density plot for females here in the red and the background we see here is much more concentrated, or is much more spread out. Sorry, we don't have that clear preponderance of cases in the 40 range. It's much more spread out. We've got a much wider representation in the range of, say, 15 to 25, which again will be reflected as we go through the course. We'll do more analysis on this and see how part-time work and gender interact. So this allows us to see where some of the key differences are emerging in gender and working hours. A much higher concentration of cases for males in the 40-hour range. So the male data is much more clearly sort of, or the more typical value is around the 40, whereas it's much more spread out for females around, we see here particularly in the lower range, but also again compared to males much less or a much lower proportion of cases in the 40 range. So those are the principal graph types for summarizing data measured at the interval and the scale level. In the next video we'll look at how we use box plots, and we'll look at how we combine two or more variables by using scatter plots.